Okay, so off we go. Thank you all for coming. Good to see you. So new topic for today, we're going to talk about surface integrals. There's a lot of analogy between this idea of surface integrals and stuff we've already done. So in particular, we've already talked about line integrals, right? And the big idea of a line integral is that, well, it's kind of dimensionally out of place, but still we want to chop it up into little pieces and make whole as the sum of the parts arguments, right? So we had to come up with a new kind of an integral. Well, here we are again. We have I wanted to be in highlighter mode. We are looking at a domain that is dimensionally out of place. It's just now it's two-dimensional instead of one-dimensional. But it's still dimensionally out of place as it's living in a higher dimensional space. It's living in a three-dimensional space. But look, if there's a mass distributed over this surface, how would we get our hands on the idea of the total amount of mass? Well, we chop it up into little pieces and argue that on each piece we can compute how much mass, and then we add up over all the pieces. I mean, so anyway, so here's the big picture construction. This is a Riemann sum. And sure, you're adding up over all the pieces. And then on each piece, say a little piece like this, the amount of quantity of whatever it is we're interested in there is, well, quantity per unit area times area. Right? If you're interested in mass, and this is mass per unit area times area. If you have ants crawling all over your surface for whatever reason, well, then how many ants are there? Well, ants per unit area times area, right? And so then, of course, you're just adding up little small populations of ants. Okay, so the notation here I think is pretty believable. You'll notice the kind of the pattern of familiar notational conventions. Just kind of following the pattern. It's exactly what you would expect. And then with the terminology as well, we're going to call this a surface integral because it takes place on a surface, right? Just like when we were doing an integral on a curve, we should have called it a curve integral, but it gets called a line integral, and sometimes called a path integral. But anyway. So this is on a surface, they call it a surface integral. Now, a further little detail, we're going to call this a scalar surface integral because the differential is a scalar, and also you'll notice the integrand is a scalar. And you can probably guess, but we're also eventually going to have a different kind of surface integral. We'll get to that in a few minutes. Okay, so this is all well and good, but this is pretty pie in the sky. How do we actually compute one of these things? How do we get our hands on it and turn the crank and answers, So good news, we actually already have all of the parts that we need to assemble how we actually compute one of these things. Because we've already studied little pieces of area on a surface. We did that last time. We were preoccupied trying to understand surface area. But the point is, we know how to rewrite little piece of area in terms of parameters S and T. And in particular, that amount of surface area is just magnitude of capital N times ds dt. It's the same exact thing as in that previous context. So ds being magnitude of capital N times ds dt, that's exactly what we needed to make sense out of a scalar surface integral. And note now our scalar surface integral has now been, that takes place over the surface, has now been pulled back and is now an integral that happens over here in the ST plane. All right. One little detail. It's always a little bit disconcerting when something that ought to be independent of the parameterization, like a surface integral, the value of the surface integral, how much mass there is on it, should be independent of how you choose to parameterize, right? So why does the formula seemingly depend on the parameterization? Remember X right there, that is your parameterization. Remember further that the normal vector, in fact, comes from the parameterization. So much in this integral depends on the parameterization. Doesn't seem like it ought to. And the good news is that's just a kind of a computational illusion. The neat fact here is that this integral here is independent of the parameterization. So it looks like the parameterization is going to matter, but it doesn't. So knock yourself out, parameterize however you like. Okay, now let's get our hands dirty and do one. We have a surface, upper unit hemisphere. We have mass distributed over that surface, like so. So the higher you are up, the more mass per unit area there is on that surface. And grand total, let's compute the mass, and I'll come to the rest of the requests in this example we'll get to in a minute. So starting with the mass. Okay, I'm going to compute with the following argument. I'm going to say the whole is the sum of the parts. Scalar surface integral is going to compute the mass for us. Here's how we're going to compute the scalar surface integral. Note that everything in this expression depends on the parameterization from which I will need to compute various partials, which I will then have to cross to get my capital N vector, which I will then have to take the magnitude of in order to get the factor that actually goes into here. But it all starts with the parameterization. So let's, per that, parameterize the upper unit hemisphere. And there you go. Now this is a parameterization we've used in the past. Keep in mind, if you're talking about the unit sphere, that's easily written in spherical coordinates as just rho equals 1. Right? And that means it's a spherical graph. And if it's a spherical graph, you can use, as I've done here, the spherical graph parameterization. So the unit sphere being rho equals 1, this is just, I've put a 1 where rho used to be. All that's happening there. Okay. Alrighty. Now, as noted earlier, once you have your parameterization, then you got to take various partials, and then you have to take the cross product, and then you have to take the magnitude, and yada, 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 a bunch of details. And again, I'm leaving this as an exercise for y'all. I showed you some of the highlights of that in a previous example last time, right, in the previous section. But if you haven't already done it, I think it's a healthy exercise to go through all those details and make sure that you can compute correctly that this magnitude is sine phi. Very classic calculation and not that bad. Again, the Pythagorean trig identity kicks in several times very nicely. Okay. So now that we've got that done, it's really a matter of kind of plugging and chugging. So here we go with the computation of mass. My very first thing to write down, I've mentioned this before, but this is my little ritual, you might say. I like to just recognize literally in writing down my first equation, the whole is the sum of the parts, right? It just looks nice on the page. So I think it's a good sort of foot in the door for the calculation. Then you can recognize things like, well, mass is density times size. And here's our standard formula for how to compute ds, right? Magnitude of capital N, d phi d theta. Let's see, we were given in the statement of the question, actually, why don't I do, here we go. Given in the statement of the question, delta is z. So there you go, delta is z. Let's see, we've already computed our stretching factor is sine phi. And the only other thing to be figured out, to be plugged in for, is, well, what is this z thing? And again, it's really easy to lose track of this, but don't forget, the parameterization itself is directly telling you x, y, and z as functions of your parameters. So specifically then, that means that cosine phi is your z. Everybody's good? And now you've got an integral plug and chug. Now, there's various other things you can compute. Let's talk about the center of mass. I'm going to talk just about the x-coordinate of the center of mass. And again, we have a standard formula for that. It's exactly what you would think it is, following previously discussed examples. And notice a lot of the development is the same. All this dm business develops exactly the same way, not even a little bit different, because they're using the same surface for which we use the same parameterization, which has the same partials and the same normal vector, and therefore the same magnitude, and therefore the same stretching factor, and therefore the same formulas for z, and etc. It's just kind of all the same, with the one difference being that here, of course, we have an extra factor of x. Of course, that extra factor of x, you can see exactly what that is. Again, the parameterization itself shows you what the values, what the expressions are, the pullback expressions for x, y, and z. So x is sine phi cosine theta. Yeah?
Will the center of mass always be, will the center of mass integrand always be x dm? Instead of
Yeah. That's right. For if you're talking about the x-coordinate of the center of mass, that's right. So center of mass is always a weighted average, and a weighted average always means that you're going to be that means that x is going to be your integrand in some sense, at least in this sense, right? And then the masses are the weights. Yeah, totally. So whether it's a double, whether it's distributed over an area or a three-dimensional region or a surface or a curve, it's always 1 over the mass, integral of x times the dm.
Okay, yeah. And this is just for the x center of mass?
Correct, that's right.
Okay.
Here we're computing just the x coordinate.
Okay.
Yeah, that's right. Yep. Yeah. All right. Okay, exercises for y'all. If you want to see more examples of this kind of thing, I've got the moment of inertia around the z-axis, it looks like, over there on the left, and a different coordinate of the center of mass here. So again, everything's a little different, mostly the same. Okay. So another example. Let's compute this thing called flux. Now, we already have, right? But recall the previous calculation that we did for flux assumed that I had a flat surface and that my vector field was constant. And of course, in the real world, that's not always the same. That's not always the case. If you want to use this formula then, how would we adapt that formula to a scenario where maybe our surface isn't flat like this, and therefore that formula doesn't make any sense anymore. Or maybe our vector field's not constant. Maybe our vector field varies. And again, that means that formula over there doesn't really make any sense anymore. That was weird. Crow fight out there. All right. So how are we going to deal with that? Well, you can probably imagine, as with everything else we've ever done in this class, we're going to make a whole is the sum of the parts argument, right? This is the wonderful thing about accumulating quantities. If a quantity is truly an accumulating quantity, then you can chop up the quantity in question into pieces and just deal with one little piece at a time and then figure out some way to add them up. So here we go. We've got this whole surface, and I'm going to chop it up into little pieces on which they're small enough that they're approximately flat. There's not enough distance inside of that piece for it to have had time to really curve very much. And where the vector field is approximately constant, because again, it's small enough that the vector field hasn't had enough time to really change any significant amount. And again, in the limit and round off errors and stuff like that. Okay. Now, there is a detail that we need to worry about. The detail is that flux is not really quite as simple as like mass or population, because there's a direction that's intrinsically part of it. If I say I want to talk about the fluid flowing through this surface, there is something fundamentally opposite about the fluid flowing that way versus the fluid flowing this way. These are clearly some kind of negatives of each other. So if we have two things that are negatives of each other, one of them needs to be, I need to have a clear sense in my mind of which one is the positive one, which one's the negative one, right? And so that has to be indicated somehow or another. The indication is going to be by way of what we call an orientation. An orientation is a collection, I'll say a consistent collection of what we'll call orientation unit normals. Just unit normal vectors whose job is just to indicate what is the positive direction through the surface. That's their only job. By consistent, I mean hopefully satisfying, but I can't have the orientation be that way at this point, and then right next to it have the orientation be the opposite way. That just doesn't make any sense, right? It needs to, in some sense, as you drag the normal vectors along the surface, there can't be any sort of discontinuities. You can't just, oh yeah, we're going to just jump to the other way, immediately. Okay. All right. So altogether, collection of all these orientation unit normals is called an orientation. And altogether then, this is now not just a surface, this is an oriented surface. And if you want to talk about flux through a surface, it really needs to be flux through an oriented surface. So that we know, what are you talking about? What is the positive direction? So just for analogy purposes, let me point out that we've actually seen something kind of like this before. Here I have some space. Let me draw a picture here. We have previously talked about curves. And we've talked about computing work with a vector line integral. Well, if I'm going to talk about a vector line integral to compute work on a curve like this, which way are we going? Right? If I'm going uphill, that takes a lot of work to go uphill. If I'm going downhill, then I ride the brakes on my hybrid car and charge my battery as I go, and I effectively perform negative work. So there's a minus sign difference between the values of work depending on which way you go. So we, again, in order to make sense out of that, we define an orientation. And an orientation on a curve is defined by, is defined by our unit tangent vector, right? And again, a consistent choice of unit tangent vectors, and it'll be, different vectors at different places, of course, but all indicating the same direction along the curve. Okay. Here we go. All right, so with that noted, with our orientation established, then here's how the calculation goes. Again, flux is an accumulating quantity that holds the sum of the parts. My little ritual, I like to write that first. Just think it looks nice. Foot in the door, non-controversial, right? It's always easy, it's always right, always leading you in the right direction. And then on any given little piece, if we're interested in, the amount of flux through this one little piece, then we just use our old formula. Easy old formula from chapter 3. And all we have to know is how big is the piece. That's the area. And then we have to know what is the vector field and how does that dot with our normal vector, our orientation. So that's just, again, a callback to chapter 3, thus allowing our d phi to turn into that, and we have ourselves a new kind of an integral. Okay. So now I'm going to talk about an alternative notation to this. This is fine, I suppose, but here's something that's awkward about how I have this written. Do keep in mind that we have a surface that is our domain. And when you talk about the differential of an integral on a domain, I feel like the differential's job is to describe everything relevant that's needed to understand that piece of your surface, or that piece of your domain, whatever the nature of the domain. So it's tempting to say, all right, well, here it is. The ds is, and it finally died. Okay, all right. Today was an experiment. I wanted to see how long this would last without charging, pretty good. I do want to get it plugged in, though, so that I can return to using it in just a moment. Sorry for the little quick delay here. Let me pop that in there, and I hope I have enough fingernails to get this thing out of here. What, I can cheat and use this thing. Nope, doesn't fit in there. Use this real quick. Golly. I'm sorry for the delay. They make this thing. I think I'm just going to have to tear this thing off. And I don't think this little cover actually serves an actual purpose. There we go. I got it. Okay. I guess it just keeps the dust out of there or something. But anyway. Okay. All right. So here we go. ds it's telling me how big my piece of surface is, isn't it? Here's the problem. That is not the only thing that I need to know about my piece of surface. I also need to know, is my piece of surface arranged in space like this, or maybe it's sitting like this, or maybe it's sitting like that, or maybe it's there's endless different ways that this could be oriented, all of which are entirely described by the normal vector, right? So I also need, in addition to ds, I need to know what is my normal vector. So in other words, I feel like n times ds ought to really be the differential. And with that in mind, I am going to rename n times ds. I'm going to call that our ds vector. And now, in one notation, I have everything that I need to know about my little piece of surface, and then the vector field alone, by itself, I can view as my integrand. Now, you might say that looks a little bit weird, that seems arbitrary. Let me point out where we've seen this before. We've seen this before when we did a calculation of work. Let me write that out here. So we computed that work. Again, the whole is the sum of the parts. And on any given little piece, one could write it, and we have several different ways to write this, but we could write it as F dot T ds. And what did we do, or what would we like to do? What, in some sense, have we effectively done concerning our little piece of curve? Well, the ds tells you how big that piece of curve is, but then you need that tangent vector to tell you how it's oriented. So we took a product like this and we rewrote it just like we did over here, thus allowing our integral to look like integral of f dot dx. Right? So chronologically, this isn't how it played out. Chronologically, we wrote down the dx first, and then pointed out, well, you can interpret dx as TDS. Right? But certainly, for analogy purposes, it still works to think of it the other way here. Sorry. I just wanted to erase that mess. So notice, for analogy purposes, again, the orientation combined with our size differential incorporates to give us our, what I like to call, vector differential. Right? So dx is our vector differential for vector line integrals. What I'm calling ds vector is our vector differential for surface integrals. Is that cool? Everybody happy? Everybody see the analogy there? Okay, so we're going to call this a vector surface integral. Again, why we call it a surface integral, I think, is pretty clear. It takes place on a surface. We call it a vector surface integral because the differential is a vector and the integrand is also a vector. Okay. All right. So let's talk about how to compute these things. Again, good news. We already know. We have everything that we need to be able to compute these things. It's right there in front of us. We do have to kind of combine a couple of things together. And now, anyway, let me not get ahead of myself. Recopying from the previous page. This is all from the previous page. We just talked about this sort of connection of ideas. And let's just remind ourselves, what do we know? We already know that this little piece of area, ds, is magnitude of capital N times ds dt. That's old news. Again, from last time. And now look at what we have here. Let's look at this expression, this product. We've got a unit vector pointing in the normal direction times a magnitude of capital N. Let me say that a little bit differently. This product is pointing in the direction perpendicular to the surface, just like capital N. Its magnitude is the magnitude of capital N, just like capital N. Kind of seems like this thing here ought to just be capital N, doesn't it? Now you probably see my little asterisk over here, right? So that's important. I have, in fact, just committed a math crime, and I'm going to fess up and apologize later, right? The math crime that I just committed on purpose is deliberate because I don't want to get distracted by a subtlety while we're right in the middle of just trying to get a formula. Let's get one done so we can see how this stuff works. And then I'm going to come back and deal with the subtlety later. Okay. Anyway, so check it out what we've got now. We have that if you want to compute a flux, we have a formula here that comes straight out of a parameterization. Just parameterize your surface. Capital N is computed directly from the parameterization. The vector field that was a function of x, y, and z can be written through the parameterization as functions of s and t as well. Everything here can be written in terms of s's and t's. This is a plain old double integral. Totally doable. Okay, again, let's get one under our belts. And we'll come back and worry about subtleties. So we want to compute a flux. So there's the formula we just derived. We're going to work with that. We've got a vector field. We've got a surface parameterized. Cool. The vector field. Vector field F here. My claim is this. No, it doesn't look right. I mean, what happened to the z's and the x's and the y's, right? So I need to take my vector field and rewrite in terms of s's and t's. So where did all this s and t business come from? Don't forget, x's, y's, and z's are given by the parameterization, right? So, for example, this z right there it is. S squared plus t squared. Everybody happy? Likewise, what's the deal with this x right there? Well, there it is. It's just S. Thank you, parameterization, right? That's what the parameterization allows me to do, is just plug in for X, Y, and Z, etc. Is that all right? Now, of course, I also have to take my parameterization. By the way, I hope it was clear. I should have said so, but notice this was being a graph. I used the graph parameterization. Right? So that's our first kind of knee-jerk choice for a parameterization, if you possibly can. It's a really great choice. So we're also going to need to know what the deal is with capital N. And so what is capital N? Well, capital N is a process. You've got to start with your parameterization. You got to compute the partials. And then you have to take the cross product. All right, that's our definition for capital N. Again, call back to last time. And then here it is. That just goes right here. So this capital N right there. Is everybody good? All right, one last little detail before we move along and talk about the subtlety, and that is what's the deal with the bounds? The giveaway about the bounds is it says above the unit square. So the first case I'll make is because it says above the unit square. What that means is I'm interested in the portion of this surface where x and y range over the unit square. So above means like this, and so sitting above the unit square, that means it's the unit square down in the xy plane is what we're looking at. So x and y need to range over the unit square. What does that mean about s and t? If x and y range over the unit square, what do s and t do? Well, here's the good news. X and y are s and t. So if x and y range over the unit square, then s and t range over the unit square, and that means that my s and t bounds are like so. Does everybody buy it? Everybody comfortable? Yeah, cool. And then so a double integral, easy double integral, polynomial integrand, constant bounds, easy integral. Hardest thing about this integral is the fractions, right? So make sure you can do that, of course. Okay, so let's talk about the big math crime. What happened here? What's the problem with all of this? It's a little bit subtle. It has to do with the question of how parameterizations matter. We know everything we've seen in the past, parameterizations have basically not mattered. I guess they kind of sort of mattered when we were doing line integrals. We had to make sure that you parameterize the curve in the correct direction. And let me say that a little bit differently. I'm going to draw a quick picture of a curve. Yeah, okay, that's fine. Again, so here's a curve, and if the curve is understood to be oriented in that direction, when we parameterize, the parameterization has to go that way. All right, well, what does that mean? What that means is that as t increases, I need to be doing like this, right? And so, you can kind of visualize that in different ways. The nice thing about parameterizing a curve is you think of the parameter as being time. You think of the parameterization as actually indicating a motion, because position is a function of time. That's literally a motion along the curve. And so when we say parameterize in the correct direction, just make the motion going the right way. It's as simple as that, right? Now, how do you know which direction your parameterization is going? Well, that's usually a pretty simple matter of just plugging in and seeing where is t equals 0 and where is t equal to, let's say 1, I don't know, whatever your ending value is. And it's usually pretty clear, right? Okay. An alternative way to say that is that for whatever parameterization you make, at any given point, x, you can compute the velocity, and that velocity vector will point in the direction of the parameterization, right? So you don't even have to have sort of a geometric or physical intuition for your parameterization. The velocity you can straight up plug in and compute, and that points in the direction you're going, and you just have to make sure that the direction of the velocity matches with the direction of of whatever is the actual orientation on the curve. Okay, all right. So ultimately, that's the problem that we have to worry about here now with surfaces. And I totally swept it under the rug, and it's easy to lose track of it. But there is a totally analogous thing with surfaces. Now, it doesn't feel like it, because when you write a parameterization, I mean, here's a parameterization of a surface. And once you have a parameterization, then you can talk about its partials, which means that you can talk about its capital N vector. And if you think about it, which direction that capital N vector points indicates a direction through the surface. But we don't have any immediate sort of intuitive, like eyeball glance at your parameterization to realize which direction the normal vector is going to be. It's just not visually obvious. We don't have a convenient metaphor like, our parameters. Parameters, time, parameterization is basically motion. No, we have two parameters. We can't, there's no analogy there. We just can't visualize. But it remains that in the same way that a parameterization of a curve intrinsically gives you an orientation, likewise, when you parameterize a surface, that intrinsically picks an orientation, kind of at random. Right? Because the actual surface, if you think about, when you're given a question, the actual surface that you're supposed to be parameterizing came with its own orientation. And again, we talked about that. When you have if you want to talk about motion through, fluid passing through a given surface, well, it has to be an oriented surface. It's got to be oriented one way or the other. So the problem that ultimately, deep down, the problem of the crime that I committed is that I just assumed that when I parameterized, I would be parameterizing with a direction, an orientation that was the same as what I was given. And yet I just made up my parameterization. I didn't in any way account for the way I was supposed to be parameterizing it. I just made it up and ignored the matter throughout my calculation. So with that in mind, here's the mistake I made. Here's the little math crime. All of this here, at this point in the equations on the couple pages back, this is all oriented as understood by the statement of the question. In other words, my given oriented surface came with an orientation unit normal vector. And then I just claimed that was going to be the same direction as the capital N, which of course is determined by the parameterization. Right? So I was effectively, when I claimed that this green equals to this blue, in effect, I was just assuming that the orientation that came with my surface and the orientation that I made up with my parameters, I was just assuming those orientations are the same. And that's completely irresponsible. It's completely unjustified. Right? When you make up a parameterization, you have no idea at a glance which way this normal vector is going to go, and no idea if it is or is not going to be the same as what it was supposed to be. So that was the mistake. That was the problem. And we're going to have to worry about that. Yeah. Mm-hmm.
So in the picture above with N and the excess, so we would. Are you saying that we wouldn't be able to tell whether capital N is going into the border, out of the border?
What I'm saying is you can't tell until you actually compute it.
Oh.
Right. In other words, when you write down your parameterization, like, you know, if you say, hey, I like graph parameterizations, I'm going to write down a graph parameterization. Who knows, right, which way that's actually going to be oriented? You can't really immediately tell from the equations other than to simply try to sneak peek, you know, maybe kind of do the calculation in your head or something. In effect, you have to compute capital N to see which way it's oriented.
Okay.
Yeah. Anybody else? Okay, so how are we going to deal with it? Oh, let me go back to over here where my initial statement of the crime here. And effectively, you can view this as having resulted from this, which came from that, which of course is just otherwise denoted by this. Altogether then, let me get rid of that's a lot. Effectively, this calculation gave me this formula for the ds vector. And this formula that says that the ds vector is capital N ds dt. Well, notice that includes my mistake. So this formula, that ds vector is equal to capital N ds dt, that presumes that you've oriented things directly. ds is oriented according to the given surface. ds does not depend on your parameterization. It is intrinsic to the surface. Capital N is not intrinsic to the surface. Capital N comes from the parameterization. So claiming that these are equal is just not quite right. So I'm going to fix that first, and here's the fix. Instead of saying that ds is capital N du dv, I'm going to throw in this extra factor of, well, it's either a plus or a minus, and I don't know which one. It just depends on, did I coincidentally parameterize correctly, or did I parameterize upside down, backwards, or however you want to say it. Now, of course, if I parameterize backwards, if I parameterize upside down, that just means my normal vectors are all the exact negative of what they should be. That means my answer is just off by a factor of -1. That's all it is, right? It's easily fixed. You just have to constantly be on the lookout for whether you parameterize the right way or the wrong way. Let me show you how that plays out in practice. So here is the same example that we saw previously, almost exactly the same example. One very slight difference. This one is now oriented downward, right? So now we want to compute, downward flux, or said differently, downward oriented surface. How do we account for that given downward orientation? Okay, so there's various different ways you can do this. One way to do this is to try to anticipate which direction you're orienting when you parameterize. I do not advise this. It's a lot of trouble, and it buys you very little. So what I'm going to advise is parameterize however is most convenient. I like the graph parameterization when the opportunity presents, most of the time. There are a few exceptions here and there. But parameterize however you like. Then take the appropriate partials. Do the cross product to see your capital N vector, and then pause. Don't proceed past the calculation of your capital N vector until you address the orientation question. And here's how that goes down. I can see now that my parameterization, here it is. My parameterization that I chose has, with no intention on my part, has parameterized what I'm going to call upward. Right? You can see in the z-coordinate here of my capital N vector, this is positive. That means these normal vectors are somewhat up. Now, they're not straight directly exactly up, right? But there's the x and y coordinates, yeah, whatever. But these are somewhat upward, and that's not what we were supposed to do. Our surface was given as oriented downward, and so here's where I can first recognize I was supposed to orient downward. I accidentally oriented upward. These are not the same. I have oriented the wrong way. And as a result of orienting the wrong way, when I come down here through the rest of the calculation, I can just recognize, yep, I'm sorry I screwed up. I parameterized backwards. There's my minus sign to make up for it all, and then proceed along with the rest of the calculation. Does that make sense to everybody? Okay. So again, don't try to anticipate it. The only thing you could possibly gain from trying to anticipate in advance that this was going to be wrong is you just save yourself having to kind of glance and see and then just fix it with a minus sign. It's an easy thing to fix, right? It's not worth trying to make sure you get it right from the very beginning. Okay. Now, a couple comments, procedural comments. Do keep in mind that this is not a class about answers, it's a class about ideas, and so you have to explain your reasoning, and in particular, if you're doing a calculation like this, you can't just stick in a minus sign right here, unexplained, mysterious, magic minus sign just showing up in your calculation. That's no good, unacceptable. Right? You got to actually give me an explanation. This is a significant and subtle, sophisticated point, right? About orientation. This is a big idea. You got to explain it. Right? Now, how you explain it? Good news. It doesn't have to be all that much. I think, for example, in this case, I can just kind of circle these together. Clearly, I'm comparing the given required downward orientation with the inadvertently, accidentally arranged positive z, upward orientation, and perfectly obvious that these are incompatible. And then you could just draw a line like this to the minus sign that you've added in there to account for that. I think this is very transparent, full credit, highly acceptable. So, not that much necessary, but you gotta give me something. Does that make sense? Everybody's happy with that? Yeah. Okay. Right. Let me show you what you can't do. I want to point out that, again, it's not about answers, it's about the argument. It is not okay to throw in the minus sign in a random place. Right? And there's a couple different random places that students, for some reason, seem to like to just kind of toss extra minus signs in, and this is not okay. You can't, for example, just throw a minus sign right there on the formula for capital N itself. Capital N is a very well-defined thing. It's the cross product of the partials. It is what it is. It's not... It's tied to the parameterization, right? So that doesn't work. You can't just kind of throw the minus sign on there. Now, again, in terms of the answer at the bottom of the page, yes, that will have the same effect on the answer, not what we're interested in, right? To me, this is two mistakes. If you put the minus sign there, but not here, then to my eyes, your normal vector is wrong by a minus sign, and your claimed relationship between ds and capital N also wrong. To me, this is two sign errors. Right? So, because again, capital N is not plus or minus the cross product. It's the cross product. ds is not capital NDSET. It's plus or minus depending on the orientation issue, right? So don't put the minus sign in the wrong place. Doesn't work. From a reasoning standpoint, and again, that's what this class is about. Okay. Then real quick, super quick, super duper quick. Also, please don't do this move that I see a lot, where students will have it down to here, and then they'll, compute, and they'll get an answer like 6, and then they'll think, I forgot orientations. Oh, shoot, my blah, blah is wrong, and then they'll just say equals minus 6. Totally unacceptable. Out of the question. Oh, my God, unacceptable. Any high schools that allowed 6 equals negative 6 on the page in any way for any reason, that's not right? This is a huge philosophical problem, if nothing else. So let me put a big red X through that. So you got to think through very carefully and make sure to understand what is part of the orientation of the original surface and what comes from the parameterization, and put the minus sign where you shift from the one to the other in recognition that you parameterize backwards. Y'all have a great Thanksgiving break. See you later. We'll pick up here next time. So Monday, a week from today. See y'all later. Have a good one.